Okay, guys, let me start by asking you a question or a survey. So today we're doing the primal dual interior point method. Next week, actually, I'm gone, unfortunately. I'll be traveling to give a talk, and you're going to have a guest professor coming and giving the lectures, the 2 Newton lectures next week. And I put the slides already up in case you wanted to look at them. I think these topics are really cool, and it's a shame I can't be here to talk about them, but you'll have somebody great coming in and talking about them. And that'll finish off our second order methods unit. So at that point, you'll have learned, I'd say, like the bread and butter. You've learned all the kind of important classic theory, and you've learned the important classic first and second order methods, and really not so classic stuff too, like acceleration and proximal Newton and proximal gradient and stochastic gradient. Those are all kind of more modern as well. After that, we're going to move into advanced topics, and I haven't set all the advanced topics yet. These were just stuff that I've either taught in previous years or I've thought could be fun to do. Some of this is like a must-do. I think some of these things are topics that would not be covered in a classic optimization course, but they're a must-see for people, I think, who are learning optimization now. Like I'd say coordinate descent and ADMM are like must-do. They're just things you really should know after taking this course. So those are not negotiable in some sense. Other ones I'm not so married to. And so I wanted to take a poll, actually at this point just about the first one. I've taught in this course before an entire lecture on numerical linear algebra. In some sense, it's a bit going backwards because you're learning all these fancy methods for solving complicated convex optimization problems, like maybe culminating with the primal dual interior point method. This is in some way what we're talking about today, the most sophisticated method applied to the most general problem. And then this lecture is about solving linear systems. So it's kind of, you're moving backwards in some sense. You're going to a much simpler problem and talking about something much lower level. But the reason I've taught that is that, oftentimes I don't think everybody sees, they don't necessarily have the same comfort with computational complexity as associated with solving linear systems. So I've been saying that, for example, solving a dense linear system is order n cubed. If you're not familiar with that, then this lecture kind of shows you why that is, and also explains to you why it is so advantageous to solve, let's say, sparse linear systems over dense ones. So I think it's a nice thing to know. It's a little bit more basic in some sense. Like I said, we'd be going back a few steps. But I'm not married to it at all, especially if most people know the basics of numerical linear algebra, like what is the complexity associated with solving linear systems, what are the structures you use to solve linear systems, et cetera, et cetera. So let me just first do a show of hands. How many people have learned things like Cholesky, QR, conjugate gradient, this stuff in other classes? Raise your hands high so I can see. Okay, and how many people have not and don't know what that is? I think that's actually, it seems like it's more than half who haven't seen it. How many people who would be interested in having a lecture on that? And hopefully, okay, so that makes it easy. I guess we'll keep that one. Right. Maybe we can vote on these later. I mean, I'm not really sure about these 3. We can vote when it comes to closer to the time as to what we want to hear. So I guess we'll just plan on doing all of this. I might put in Frank-Wolf as a must-see too. So these 3 topics, Frank-Wolf, coordinate descent, and ADMM, are very, very popular methods today, and they all have kind of like huge practical importance. Okay, so today we're talking about primal dual interior point methods. It's our second interior point method lecture. And let me get out a pen. So like the barrier method, the idea behind the primal interior point method is also going to be to follow something like the central path. Right? So the canonical example we think about with interior point methods is linear programs. So suppose I have some LP, right, where I'm minimizing, let's say, C transpose X, subject to a bunch of, let's say, inequality constraints. d times x less than or equal to e. That defines some polyhedron, some convex polyhedron like this. Okay, maybe the solution is here. Okay, maybe C points in some direction like here. This is the direction C points. And we define some kind of central path. Right, so maybe starting, let's say, at 0, we're going to be defining something called the central path. In fact, it's the same central path you saw last time, but we're going to be looking at it from a slightly different perspective, which is the perturbed KKT conditions. And the end of the central path is going to be the solution we care about. Okay, and the name interior point methods reflects the fact that we are approaching the solution from the interior of the constraint set. Okay, so we're going to be taking steps that kind of are very close to the central path. They're not going to be exactly on the central path in practice because we're going to be using something like a Newton step here. And the Berry method also had a very similar interpretation. We were following the central path. We're just progressing in a different way. That's the difference between the primal dual and the barrier method is kind of how we traverse the central path. But in either case, this is the picture you might want to keep in mind. Okay, we're approaching the solution via something called the central path from the interior. Okay, right. So last time, I'll just recap what we talked about last time, the barrier method. So this was the problem we thought about solving, a very generic convex problem where we had criterion function f, inequality constraint functions hi, and linear equalities ax equals b. We assumed that f and hi are all convex and twice differentiable. And we actually assumed there was a point x for which hi of x was strictly less than 0 for all I. And that implied strong duality, right? Because that implies that Slater's condition holds, the problem is convex, and there's a point that satisfies all the inequality constraints strictly, and then we know that strong duality holds. And we considered this problem that we called the barrier problem, okay, which is equivalent to, by the way, this problem, which is sometimes the way we think about it. It's just moving the t over to we're moving 1 over t over to the barrier function. Okay, and this had no inequality constraints. And we thought about this function phi, okay, as a smooth approximation to the indicator function. Right, if I replaced this phi in the criterion by the sum of, maybe this was our original problem, I could have written the original problem as the sum of over all I of the indicator that hi of x is less than or equal to 0. Then I wouldn't have changed the problem. So this is the original problem. This is the barrier problem. And the barrier problem just forms a smooth approximation to the indicator. And the larger t is, the better that approximation is. Okay? And the barrier method basically solved this problem over a sequence of values t, which is equivalent to just putting the t in front of the f. Okay? So specifically, the log barrier function is minus the sum of log of minus hi. Okay, and so we saw by looking at the KKT conditions for the barrier problem, and by defining a particular pair of variables u and v, which we call dual variables, we showed that those dual variables, which can be defined in terms of solutions to the barrier problem, they actually give us a duality certificate. So they give us essentially a duality gap, okay, of m over t. So that if we were to solve this for any value of t, the difference in our original criterion f at the solution which we called x star of t and the optimal value f star in this problem was at most m over t. Something we proved last time. So this motivates essentially solving this for larger and larger values of t, because we can see that from this equation that in the limit we're going to get something that's optimal for this problem, our original problem. So it's indeed kind of making rigorous the intuition that this is approximating the indicator. As we take t larger and larger, that approximation has error that's vanishing So the solutions here will approach solutions there. The difference between the barrier method and what you might have tried at first pass is that the barrier method actually has you solve this over a sequence of values of t and kind of gracefully increases t. It just doesn't jump to a very large value of t. And every time that you solve the problem, you use Newton's method and you warm start the solution at the current value of t with what you arrived at. Sorry, you warm start the algorithm at the current value of t with the solution you arrived at the smaller value of t. Okay, so we start off at some value t0, we optimize to get x0, and then we move t up to t1, multiplying by some constant mu that's bigger than 1, like think about 10, for example. And then we run Newton starting from x0, and we're going to arrive at a solution x1, and so on. Okay, maybe this Newton solve started at an arbitrary point like 0. So that's the barrier method, right? Every time we multiply again by mu, we get a new value of t. We start at x1, we run Newton to get x2, etc. And we know from what we showed last time that we could stop this algorithm at any point, and the current value of t is going to give us a duality gap via m over t. So we could, in fact, if we had some prescribed number of, or some prescribed number epsilon of desired suboptimality, we could just run until m over t is less than or equal to epsilon. Okay, so that was the barrier method. Roughly speaking, and this is something that we didn't prove, but I referred you to some work on self-concordance that makes this precise, or also the Boyd and Vandenberg textbook, which does it more generally, but in a less clean way, without self-concordance. This updating scheme, multiplying by mu, it is chosen so that Newton's method pretty much always will stay in the quadratically convergence phase. Right? So I could have, instead of multiplying by mu, I could have added mu. I could have, somehow I could have raised this to a power. I could have exponentiated the t's. There are various updating schemes you might try. They all have different properties, right? Updating too fast or updating too slow, that comes with certain trade-offs. And this particular updating scheme, multiplying by a constant factor mu larger than 1, it's good for the barrier method because it A, means that the total number of iterations we're going to need is something like log of 1 over epsilon. And B, it keeps Newton in the quadratically convergence phase because you're warm starting at a pretty good value at every outer iteration. And so the number of Newton's iterations that are needed to converge to very high accuracy is roughly a constant, like 5 or 6 is the kind of rule of thumb. So that's why this updating scheme was chosen. Today we're going to talk about the primal dual interior point method. We're going to motivate it from the perturbed KKT conditions, which was an alternative way of viewing the barrier method. Turns out that you can view this construction in a completely alternative way, which we touched upon last time. Then we'll talk about the method in detail. We'll talk about backtracking, and we're going to end with a discussion of standard form LPs because this was somehow historically the problem people cared about when this all this methodology was being invented. So let's start off with a high-level difference. What's the difference between the two? There's the barrier method and the primal dual method. Both, it turns out, can be motivated from the perturbed KKT conditions. So we're going to step through that in detail just now. A really big difference between the two is that the primal dual method, it takes only one Newton step per value of t. So unlike the barrier method, which runs Newton until convergence, primal dual method takes one Newton step and then updates t. That means that there is no distinction in the primal dual interior point method between outer and inner iterations. It just has one level of iteration. Okay, and that actually makes somehow the statement, the end convergence statement, a little bit more easy to interpret because the number of iterations that it takes is really reflective of the computational cost. There's no outer and inner iteration kind of distinction. An important other distinction is that the primal dual interior point method, it produces iterates, and most specifically dual iterates. If you start the primal dual method, let's say with primal feasible iterates that satisfy these equality constraints, then you can guarantee that the iterates maintain primal feasibility but the dual iterates need not be feasible. So it does take steps in the primal and the dual, hence its name. It turns out that the steps it takes in the dual do not maintain feasibility. That's a very big difference to the barrier method, where if you maybe look at the notes from last time, we saw that at every iteration we could actually define dual iterates that were feasible, and that's what gave rise to this duality gap. This very nice kind of simple duality gap came from that construction where we had feasible dual iterates. That's not an upside, that's a downside of primal dual interior point methods, just to be clear, that it doesn't maintain dual feasibility. The upshot is that partially because it doesn't do so, and partially because one can get very clever with these Newton steps and exactly what approximations you make, they can be more efficient than the barrier method. So often in practice, it's much more efficient to use, I wouldn't say much more, it's more efficient to use the primal dual interior point method than the barrier method. And they can have, in some situations, empirically superlinear conversions. So they actually empirically converge somewhere in between this and quadratic, right? Quadratic being log 1 over epsilon. So empirically, for many problems, they're somewhere in between. And I believe even theoretically, for some problems, they have superlinear conversions. They're much less intuitive than the barrier method. So I think that the barrier method is something that hopefully, if you remember Newton's method and the barrier method, that seems like a pretty good, like minimal thing to remember for second order methods. It's pretty hard to remember the details of the primal dual interior point method. It's less intuitive. It's more complicated to learn. It's more complicated to implement. So it's more sophisticated, but the upshot is that it's more efficient. And maybe one editorial comment, this was, somehow this is like the pinnacle achievement of optimization in like the 70s and the 80s and the 90s were these primal dual interior point methods. So they were enormous deal when kind of people were working on them, and they are the main workhorse behind a ton of commercial state-of-the-art solvers for linear programs, quadratic programs, QCQPs, SDPs. The primal dual interior point method is the main workhorse. The barrier method really does not make it into, let's say, these commercial packages. So let's go back to the perturbed KKT conditions. And we're going to see that we can motivate the barrier method from this and a new method called the primal dual interior point method. So if you recall from last time, we wrote down the KKT conditions for this problem. Okay, and what we did last time, I'll just write down the workflow what we did, so you can remember where these came from. Last time, wrote down the KKT conditions for the central path problem, or for the barrier problem. Okay, and that had, let's say, a variable x and a variable w. So x was our primal variable and w was the dual variable corresponding to this inequality constraint. And then we introduced two new variables, ui, which we defined as minus 1 over t times hi of x. And this was true, we defined this for each one of the inequality constraint functions. And v, which we defined as this dual variable for this equality constraint in the barrier problem, we just scaled this by t. And we then rewrote the KKT conditions in terms of x, u, and v. And by the way, these were the two dual iterates, or these were the pair of iterates, u and v, that end up being feasible for the original dual problem, for the dual problem of our original problem. So this is where the duality gap came from, of m over t. We evaluated the dual criterion for this problem at u and v, and we looked at the difference between the primal criterion at x star of t and the dual criterion at these guys, u and v. So that's where the duality gap came from. But moreover, just looking back at the KKT conditions themselves, we arrived at these perturbed KKT conditions that you see on the slide. And it's a very interesting sequence of steps because it brought us to a set of conditions that look like the KKT conditions for our original problem, but have one key difference, which is that complementary slackness has been perturbed. So this is stationarity. This is just a stationarity condition for this problem. Right? Take the Lagrangian, and in this case, everything is differentiable with respect to x. So take the gradient, set it equal to 0. That's stationarity. This is primal feasibility. That's dual feasibility. And this guy here, in the usual KKT conditions, looks like ui times hi of x equals 0. And here we've replaced it by minus 1 over t. And as I commented last time, if we're going to perturb this condition, complementary slackness, where their product is 0, to be something that's not quite 0 but approximate, we're going to have to make this negative because ui is going to be bigger than or equal to 0 and hi is going to be less than or equal to 0 by dual and primal feasibility. So the product, if it's not 0, is going to have to be negative. And it turns out that, essentially solving this barrier problem for a particular value of t is just equivalently posed as solving the KKT conditions with minus 1 over t replacing 0 in complementary slackness. So another perspective that very large t is making this very close to complementary slackness. So their product is really small negative, very close to 0. And so solving this, it's a nearby system of equations. It's nonlinear in x, u, and v, but it's a nearby nonlinear system of equations. And so it should look like the solution to the KKT conditions where this was replaced by 0. Okay, so let's go one step further and say, let's get rid of, for the moment, the inequality constraints, and just imagine that somehow we're going to always preserve these. So we're going to keep in our mind that whatever steps we take, we're going to be preserving the signs of hi and the signs of ui to be as appropriate. And let's look at the system itself we're trying to satisfy. And let's write it as one big nonlinear system. Okay, so what I'm going to do, is I'm going to define h to be a function with component functions h1 through hm. So now this is a function from Rn to Rm. Okay? And I'm going to write its Jacobian as dh. So I think in a previous lecture, I think I actually always wrote the Jacobian as d times h. That's the Jacobian of this function. Okay, so with respect to the component functions, I have the gradient of the component functions on the rows. That's what it looks like. Okay, grad h1, grad h2, all the way through grad hm. All the equality constraints here, I can stack into one big system. So let's first take a look at the stationarity condition. I can think about this as let's say U transpose the Jacobian matrix. That's how I can think about this. Or maybe the Jacobian matrix transpose U, depending on how I want to write the sequence of conditions. Okay, and so that's what I'm writing here. I want, let's say, for every, I want to set the stationarity condition just in more general notation. I can write it as grad f plus the Jacobian of h transpose u plus a transpose v equals 0. That's the stationarity condition. Primal feasibility, I'm just writing x minus b equals 0. And this is the perturbed complementary slackness. So I'm writing the product of ui and hi equal to minus 1 over t for all I as a diagonal matrix of the u's times this h function minus 1 over t must be equal to 0. In fact, just for completeness sake, that should actually be minus 1 over t times the 1's vector. Doesn't really matter, just in case it's confusing to you, I'll write it out here. So this is the nonlinear system that underlies the the perturbed KKT conditions. And the KKT conditions themselves would actually replace this whole thing by 0. Right? I wouldn't have this minus 1 over t times the 1's vector. This would just be 0. Okay, so hopefully this notation is clear to everybody because we're going to use it to develop the primal dual interior point method. Let me pause, see if there's questions. Okay, diag of u, just to be clear, just the diagonal matrix with the u's on the diagonals and 0 everywhere else. So diag of u times hi, or times h rather, is just the vector that's ui, let's say u1, h1 of x, u2, h2 of x, etc. So that's why this is complementary slackness. Okay. So when we look at this, maybe because we've been talking about Newton already, you might have already gotten here. But in general, you might think that it would be natural to try to solve this nonlinear system, which we know is what's motivating, let's say, both the Berry method and the primal dual method, via Newton's method for root finding. So we talked about Newton's method for optimization, but in that lecture I emphasized that Newton's method maybe originally, and at its most basic, is actually a general method for finding roots of a nonlinear system. So let's suppose our system was called f of y equals 0. Then Newton's method makes essentially a linear approximation at every single iteration to this function around the current iterate y. So it approximates f of y plus delta y by f of y times the Jacobian of f at y times delta y. So this is a linear function of delta y, right? This is a linear function right here. And solving this for delta y leads to this update, minus the Jacobian inverse of the function. And what I had emphasized in the Newton's method lecture is that if you are to solve let's say, a differentiable convex problem, that's defined by this nonlinear system of equations, the gradient being equal to 0. And if I define that to be, let's say, f of x, if I take the gradient to be f of x, then the Newton update we get, which is minus df of x inverse f, that's exactly equal to Hessian inverse the gradient. Right, the Jacobian of the gradient is the Hessian. So this was really what underlied Newton's method for us, this linearization. So now that we're looking at this nonlinear system of equations, which is a system in x, u, and v that we're trying to solve, right, we could think about applying Newton's method. So just taking the Jacobian of this, inverting it, and moving in the direction of df inverse f, for f being this function, the one that gives us all this stuff. So there's two ways to do that, okay? And that leads to two different methods, one of them being the Berry method, the other one being the primal dual interior point method. So we already proved, let's see, we already proved actually, we went through this sequence. So KKT conditions for the Berry problem, introduce these dual variables, rewrite the K and D conditions, arrive at the perturbed KKT conditions. That shows that the Berry method actually solves the perturbed KKT conditions. Now on this slide, I'm going to go the opposite direction. We're starting at the perturbed KKT conditions, these ones, and I'm going to show you how to get the Berry method out. Okay, how we might have gotten the Berry method out of the perturbed KKT. So kind of the opposite direction. And what we're going to do is we're first going to just notice that this system is very easy to partially solve. Right? It's a very natural thing. If you had this system in hand and somebody said, please solve it, you would say, oh, well, look, I know that each ui has to be minus 1 over thi. This is very easy to solve. This doesn't require any computation, this middle thing. So I'm going to eliminate u. So after you eliminate u, you get this reduced system, which is just a system in x and v. Right? This is primal feasibility, and this is stationary to be written with just ui being equal to minus 1 over t times hi. So that was just a kind of a trivial rewriting. And now it turns out that a Newton update on this problem is the same as a Newton update you do for the barrier problem. Okay, and you can see that you have to just remember somehow what the Hessian looked like for this barrier problem here. So, okay, let's take the Jacobian okay, of this function. So this is a particular function we're going to call R of x and v. Let's take the Jacobian, and we're going to write it in block form. Okay, this is going to be the Jacobian times the update direction equals the function. Right, so we're just going to rewrite this Newton step. Another way of writing this Newton step is that we want to have the, I actually missed a negative, Jacobian times the step equals negative the function. So this right-hand side should say negative r xv. Okay, and now let's differentiate, let's say, this top block with respect to x. Okay, if I differentiate with respect to x, I'm going to get a matrix that I'm just going to call h bar for now, or h bar for barrier. And if I differentiate with respect to v, I just get A transpose. Okay, so that's the top block of the Jacobian matrix. Now let's differentiate this with respect to x. I just get A. And with respect to v, I get 0. So this is the explanation for why this is the Jacobian matrix of this guy, R. And now this system, I can write as this Jacobian times my delta x here is actually delta x comma delta v. It's a bigger, it's a system with two blocks of variables, x and v, equals, let's just say, minus r of xv. And what does this look like to you? This looks very much like the KKT system we solved in the inner Newton step of the barrier method. Right? In fact, it's identically the KKT system we solved in, well, while running constrained Newton's method on this problem. So equality constrained Newton's method on this problem, it exactly takes updates of this form, where h is it is the Jacobian of this with respect to x, which is exactly equal to the Hessian of f plus the sum of 1 over t times hi squared times the outer product of grad of hi plus the sum of minus 1 over t times hi times the Hessian of hi. And if you look at this carefully, and hopefully you remember a bit from last lecture, you'll see this is exactly the Hessian matrix associated with 1 over t times phi. So this is now the explanation for why this thing is the KKT system for running equality constraint Newton here. So in other words, we've reproduced the barrier method from the perturbed KKT system. Okay, so we could just repeat updates of this form. That's the barrier method. Or we could do something different, which is that we could actually not eliminate u. We could leave u untouched. And it turns out, and this is a bit counterintuitive, it's actually more efficient to not partially solve for u, because that's going to lead us to a different method, which is the primal dual interior point method, which is more efficient. It turns out it just takes better, in some sense, Newton steps. So we get a bigger system, okay, because we have u in it still, and it just, in the barrier method, often helps to write each block of that linear system as a different, with different notation, and we call these residuals. So the stationarity block we actually call the dual residual. The perturbed KKT condition block we call the centrality residual, R cent. And the last one we call the primal residual. And we're going to let y be the triplet xuv. That's going to be the variable we're thinking about taking Newton steps in. So now if we run root finding, so Newton's method for root finding on this block of variables xuv, we're going to form exactly this. Okay, the Hessian, the Jacobian of f, should say y inverse delta y equals minus f of y. That's this system here. Okay, I've just rewritten r of xuv in terms of this triplet, r dual and r central and r primal. These are my variables, delta x, delta u, delta v, and this is the Jacobian matrix of this system. Right? To see that, I'm just going to take derivatives with respect to x, okay, and I'm going to get some matrix I'm going to call HPD. That's the derivative of this with respect to x. I'm going to take a derivative with respect to u. I'm going to get dH transpose. And derivative with respect to v, I'm going to get A transpose. Okay, down here I'm going to differentiate with respect to x. I'm going to get just minus diag u times the Jacobian matrix of H at x. Differentiate with respect to u, I'm just going to get minus diag of H of x. And with respect to v, I'm going to get 0. And then finally, for this last block, for differential with respect to x, u, and v, I get a, 0, and 0 respectively. So that's the explanation for why this is the Jacobian. And the only kind of non-trivial part is, or maybe this is even not that necessarily hard to work out, the differentiation with respect to x here gives us a matrix which we're going to call the primal dual H, HPD, which is the Hessian of f plus the sum from I equals 1 to m of ui times the Hessian of hi. So that takes the place of this guy in the barrier method, okay, which was more complicated because after substituting in for u in terms of hi of x, I just had more terms to differentiate with respect to the chain rule. Right? Now I haven't done that, and so this differentiation with respect to x was simpler. Okay, so we're going to basically think about solving this big system, okay, and then just moving delta x, delta u, delta v, moving our iterate x, u, v in that direction, delta x, delta u, delta v. And that's going to be approximating the solution essentially to this system. And after we just take one step, we're going to update t. That's the essence of the primal dual interior point method. So just some notes. In version 2, the update directions for the primal and the dual variables, they're kind of inexorably linked together. So we're updating them in a very non-trivial way together. In version 1, we kind of already had set a value for the dual variable in terms of the primal variable. And so we just really take an update with respect to the primal variable, and then this is kind of deterministically what we take for the dual variable. So that's an important difference. They lead to different updates. They're not equivalent. So, let's say partially solving a nonlinear system, applying Newton's method is not the same as applying Newton's method to the original system. So they're not the same updates. As we already saw, the version 1, which did this partial solving for u, it's equivalent to one inner iteration of the barrier method. So it's another way of viewing the barrier method. And this version 2 leads to a method that we're going to call the primal dual interior point method. One complication, and this is a significant complication for primal dual interior point methods, is that the dual iterates are not necessarily feasible for the original dual problem. So that's a big complication in terms of stopping, like how we define a proper duality gap. It turns out that the u you get from this system, okay, we can control it for always being positive. We can make sure that by backtracking, essentially, that we can always keep u to be positive in every coordinate. But we can't ensure that it lies in the domain of the Lagrange dual function necessarily. Okay, it still may not lie in the domain of the Lagrange dual function, which makes it very difficult to rigorously define a duality gap. We saw that actually this does lie in the domain of the Lagrange dual function, this choice, because essentially this choice, if we looked at the solution to the barrier problem, by the way we set it up, that solution minimized the Lagrangian. So that meant that the Lagrangian was away from minus infinity at that point x, which is another way of saying that this u lies in the domain of the Lagrange dual function. We have no such kind of guarantee here. They could be dual infeasible, the u that you find here, and v. Okay, let me pause before moving on. From my experience in teaching this course, this is the lecture that confuses people the most. It's also the most complicated method. So it helps to kind of pause and just ask if people have questions. Yeah?
Why the left side right side?
Why is this inequality, you're saying?
This side right side.
Are you saying here or here? This?
Yeah.
This is a system that we're defining in order to take a step delta x, delta u, delta v. So in other words, this delta x, delta u, delta v is defined to solve this system. This is this Newton update. Okay, so I'll just write that once more in terms of a y. So I have this system, let's call it f of y equals 0. Okay, for us, f is actually r. For us, y is actually x uv. Okay, and f of y is actually r of x uv. That's actually what our problem has, this form. And we are taking a Newton step that is of this form. So delta y equals minus df y inverse f of y. In other words, we're defining the Newton step delta y in this form. Another way of writing that is just that it solves this system. Okay, and I'm just translating what that means for our problem. The Newton step for our problem, instead of looking generically like this, it actually looks like this. And I walked through the derivation of the Jacobian, explaining what each of these parts was. Does that make sense? Yeah.
So we take steps along each of these gradients and then we
We're going to move x uv in the direction delta x, delta u, delta v. And I haven't told you the details of backtracking yet, but there'll be some step size that we're going to have to choose. But that'll be the prescription, yeah. Other questions? Yeah.
For the barrier method, we effectively go through all the variables multiple times. For updating t, for us with the prime dual method, we go delta x, delta u, delta v, then update t.
Yeah, it's a good question. So I guess, like from this perspective, right? It's not clear why we need to iterate, let's say, more with this than with this. They seem to just be taking different approaches to solving the same nonlinear system. I would maybe venture a guess that the reason we do that with the barrier method is more that kind of from the motivation perspective and historically we think about it coming from an approximation to the indicator function. And we think about somehow, solving this problem to optimality before you update t, because somehow this problem is an approximation. And that's what leads to those inner iterations. The primal dual interior point method, it actually stays farther away from the central path. So that's kind of why I drew these dots. I mean, it's like a very minor distinction, but the barrier method really gets you very close to the central path. The primal dual interior point method actually kind of bounces around the central path. So you're not staying on the central path as closely. I don't really know why. I can't give a good answer for why people don't analyze the barrier method after one iteration and one update to t. But I haven't seen that. It just seems maybe the method is somehow of historical importance anyways, and we mostly use the primal dual interior point method in practice. Yeah, so just to emphasize somehow, like each Newton step is going to take us maybe somewhere close to the solution to the perturbed KKT system, but we're only taking one Newton step, so it's really not going to get us there. It's just going to bounce around the central path a bunch before arriving eventually at the solution. Other questions? Okay, this seems like a fine spot to take a break. When we come back, I will do the duality gap, and then we'll talk about backtracking and then the actual method. Okay, guys, so we're going to talk about the duality gap first, then introduce the primal dual interior point method kind of in full. So for the barrier method, as we've already mentioned, we have this very simple duality gap of m over t, and that came from setting ui to be minus 1 over t times hi of x, plugging this into, and v to be something in terms of w, plugging this into the Lagrange dual function of the original problem, taking the difference between the optimal or the criterion value, let's say at the barrier central path solution and this and the dual function at these dual variables, and that led to this duality gap of m over t. And that was valid because this u and the v that was defined in terms of w, they were dual feasible. For the primal dual interior point method, we don't have dual feasible iterates necessarily, so we don't have a nice duality gap, but we can construct a surrogate duality gap, an approximate duality gap. And essentially going through the same calculation, the exact same calculation as I just described, we could still plug in u and v to the Lagrange dual function, take the difference between, let's say, the primal criterion at x and the dual criterion at u and v, and that would lead to this, minus the sum of ui hi. That's the calculation we did last time. And when you plug in ui to be minus 1 over t times hi, this thing just becomes positive 1 over t, the sum from 1 to m, and that's where the m over t comes from. We can still do this. No one's stopping us from doing this, from just evaluating this functional for an arbitrary value of u and x. But it won't be a duality gap. It won't actually, let's say, bound the suboptimality that we're seeing in the primal unless we had feasible points, primal feasible points and dual feasible points. And so for the primal dual interior point method, we can iterate, get some x's and u's, and evaluate this. But because those u's are not dual feasible, it's not actually a duality gap. So that's why it's an approximate duality gap. As the method proceeds, if we believe the method's doing something reasonable, which it is, it's going to be getting us closer and closer to primal and dual solutions. So in particular, it's going to be pushing the dual points closer to feasible. So they're going to be very close to feasible, and in which case this kind of surrogate duality gap is going to start looking more like a duality gap. And in fact, when they're feasible, or when they're, let's say, in the limit they are feasible, this will actually be the duality gap. Feasible points means that the primal residual is 0, so I actually have something that satisfies the not sure why it's doing that. The primal equality constraints, ax equals b. I said this in passing just to remind you, we are always going to keep hi and ui to have the proper signs. That's never going to be an issue. That's going to be something that's a matter of initialization and proper backtracking. So feasibility means satisfying these equality constraints in the primal and ensuring that u and v are in the domain of the Lagrange dual function, which means that this stationarity condition is actually met at the current x, u, and v. Right? The barrier method, just to repeat one more time, I feel like I'm hopefully not too much of a broken record. The barrier method does make sure this is met because we define u and v essentially to meet this once we have the barrier solution. If this is met, then that means that at this u and v, that x minimizes the Lagrangian, which means that that u and v are in the domain of the Lagrange dual function, because the minimum Lagrangian, let's say, is away from minus infinity. Okay, but we don't know. If we just take one Newton step, we don't know that somehow this is actually satisfied. It's not going to be 0. It might be close to 0. And we don't know that somehow this u and v are therefore in the domain of the Lagrange dual function. That is why, by the way, we call this value the dual residual, because if it's 0, then we have dual feasible points. And if it's not, then we don't know that we do. And that's why the primal residual was ax minus b. It's for that reason. Okay. So this is going to be our cert duality gap. And right, if we look at the perturbed KKT conditions, if we call this value eta, in the perturbed KKT conditions, the value of t that this corresponds to is going to be eta over m. Right? It's the same reason that it's the same rationale we just made. Somehow, if this product is equal to minus 1 over t, then this sum is going to be equal to m over t. And so that's going to tell us that eta is going to be equal to m over t. So in terms of this surrogate duality gap, the relationship to t is eta over m. It's just going to help when we formulate the method. So here's the method in full. It looks very different to the Berry method because there's only one level of iteration.
That I think in the last time, I believe that T should be like M over M.
T is m over eta, and
Yeah, we talked.
yeah, you're right. It's a typo. Thank you. Yeah, so we had eta is just the, let's say, minus sum of ui hi of x, right? And if complementary slackness or perturbed complementary slackness told us that the product of these two is minus 1 over t, then this would be m over t. And that means that t is going to be m over eta. Thank you. Just a typo. Okay, which is indeed what you see here. I just had written it backwards in the previous slide. So here's the method. We fix a strictly feasible primal point. What I mean by that is that this satisfies all of the inequality constraints strictly. Hi of x0 is strictly less than 0 for all I. And we fix a strictly feasible, let's say u, dual point u. So u is strictly larger than 0. That's what I mean by that. And any v. And we're going to define this surrogate duality gap, right, just to be the minus the sum of ui hi at the iterates x0 and u0. And we're going to fix some barrier parameter mu like we had in the barrier method. I'm not sure why I call it the barrier parameter. It's not really called that here. We just fix some, let's say, update, this update parameter mu, and we're going to repeat the following iterations. We're going to figure out what value of t that duality gap eta corresponded to, okay, via this relationship. Okay. And we're going to update that value of t by mu. So at the previous iteration, we had duality gap, let's say eta k minus 1. The value of t that corresponded to was m over eta k minus 1. We're going to update that by multiplying it by mu. And that's going to be the value of t that we're using to solve the Newton system for the perturbed KKT conditions. We're actually going to solve that Newton system to compute the primal dual update direction delta y. So that's this step right here. Okay? Solve this system for that value of t for delta y, which is that triplet, delta x, delta u, delta v. And update our primal and dual variables, y, in the direction that we found by some amount s. Okay, we're going to have to do some backtracking to determine the step size s. But once we find it, we'll perform an update like this, which is just like we do in Newton's method. We'll compute the duality gap again, okay, or the surrogate duality gap again, which is this, the minus sum of ui hi evaluated at our current iterates. And instead of continuing on with these Newton updates, we're actually just going to stop with that one Newton update and update t. So go back to the first step here, update t. Okay? This is our stopping criterion in total, so we will stop the algorithm in total if two things occur. The first, the surrogate duality gap is small. So if somebody gives you this epsilon, let's say, which is a value that they're willing to tolerate for the suboptimality, we're going to stop when the surrogate duality gap is small. But that's not good enough because actually that's only valid, let's say, when things are feasible. So let's say it's only going to be approximately valid when things are approximately feasible. So we're going to check primal and dual feasibility together. We're going to check how close to B the product AX is. So we're going to take the norm of the primal residual. And we're going to check how close to 0 the gradient of the Lagrangian is. So that's how close to feasible is that dual U and V. So take the norm of that dual residual, which again is just this thing here. Okay, so we're going to measure somehow the square norm of this and the square norm of this, and we're going to stop when their sum is very small. Okay, so this is a typical stopping criterion. That you could actually have two different values of epsilon. I just tied them together here for simplicity. Okay. I wrote down here by construction we maintain primal feasibility. That was maybe I could have written a bit more to make that more clear. What I meant to say is that if we start with point x0 that satisfies ax0 equals b, then this Newton update we take is going to preserve that. It's actually going to always keep us in the equality constraints. And backtracking is always going to ensure that hi of x is strictly less than 0. So had we started with a feasible point overall, we would always have primal feasibility. That's just a matter of choice, whether we start with a point that satisfies ax equals b or not. It may be more efficient not to start with that, because maybe that requires solving a large linear system to begin with. It's really a dual feasibility that is the more kind of difficult feasibility condition. We have really no way of maintaining that. Okay, so what does backtracking look like? Backtracking looks as follows. We're going to choose a value of s, move each of our primal and dual variables in their appropriate directions by an amount s, and we want to make sure that we keep hi of x strictly less than 0 and ui of x strictly larger than 0. And we use something called multi-stage backtracking for this. So first we find the largest step size, and we're doing Newton steps here, so the biggest step size that makes sense is 1. So we can always start at 1 and figure out where to go from there, taking smaller steps from there. And we're going to first figure out the largest step size that keeps the dual iterates strictly positive. So we'll just figure out, I have some given direction delta u I calculated. I have some vector u that I have in hand. And I just look at every component. How far can I move ui in the direction delta of ui by an amount s before I hit 0? Okay, for some of them, that won't ever be a problem, because let's say this delta ui is positive. So taking steps of arbitrary size is always going to keep me positive. For those that are negative, I have to make sure that I don't go beyond this, minus ui over delta ui. Okay, because if I go beyond this, I'll make the new update mu plus negative. So this is the largest step size I can take that respects this. And then I just take something slightly smaller than that, because I want to have strictly positive iterates. So I just maybe pull off by 1/100th or something like that. And then now that I've somehow satisfied keeping the u's positive, I try to make sure that I keep the h's strictly negative. And I'm only going to make s smaller from this value that I already found for the u's. And now this is done with two kind of more traditional backtracking parameters, alpha and beta. And I'm going to multiplicatively decrease the value of s until I see all of the h's being strictly negative. And this is optional, but it's done in order. So this is all we really needed to do. Make sure the h's were negative, make sure the u's were positive. So that's the backtracking strategy, in some sense, has accomplished its goal. This is done in order to help us converge in the end, because we also want to maintain primal feasibility if we have not been keeping in the linear subspace ax equals b. So we're going to check essentially that we've decreased the residuals enough. Okay, so I'm going to look at this full residual. At the new updates, I'm going to make sure that I've decreased them enough. Okay, so a little bit more sophisticated backtracking that we've seen than what we've seen so far, but that is kind of the standard for the primal dual method. Okay, so that's our method. Let me again pause for questions, because I think people sometimes tend to be confused about this method. Yes?
So that last step on decreasing the residuals, that was to ensure primal feasibility?
It's not necessarily, it's really to ensure, I guess, feasibility. So it's to ensure that we're going to arrive at some step eventually where this is small. I had probably said it in a confusing way. If we had set ax equals b to begin with, then I guess I was just saying one of these the first component of this r vector would be 0. So it wouldn't really matter, because, or not the first component, the third component would be 0. So that would really just read as a condition on the stationarity block. But in general, somehow, one advantage of the primal dual interior point method, perhaps, is that you don't need to initialize the algorithm with something that meets the equality constraints. I can just choose an x that satisfies hi of x is less than 0. It might be an expensive thing to start the algorithm by saying, I want to find an x that meets the equality constraints and hi of x is strictly less than 0. So we don't have to do that. We can start it with just something that satisfies the h constraints. And then this backtracking, this last step in the backtracking, tries to help us ensure that in the end we're going to have things that are close to primal and dual feasible. Probably a better way of saying it. Yeah.
Primal dual method. So this is like in the direct method. If you solve it approximately, like, the reason we don't do that is you might diverge the path, you won't reach the solution. So here you're sort of like jumping around. So what makes it here that in the end, like you won't diverge something that the path actually converges to the limiting point of the central path?
It's a good question. So do I have any notes on the analysis for the? I don't have notes on analysis here. So in previous semesters, we've done 2 lectures on the primal dual interior point method, and one of those lectures has been a bit more details on the analysis. So I guess the devil's in the details, that somehow what steps you take really matters, and the updating scheme really matters. So it turns out this combination of multiplicative update that's defined in terms of some of the surrogate duality gap you're witnessing, and this particular step, the one that came from that Newton system, it stays in a neighborhood of the central path. So you can actually prove that it stays in if you kind of define a tube around the central path with respect to a given norm, this step is going to be staying in that tube. So you're not going to be diverging from the central path. And there are many variants of this, of the primal dual interior point method that are not this, that use different steps. So if I can remember the name of some of the steps. There's essentially different types of steps. They go by the name, like there's short steps and there's long steps, and there's each of them have slightly different properties in that they stay around the central path with respect to different norms. So there's a different kind of geometric notion of a tube in which you maintain. But for any variant of the primal dual interior point method, that is kind of a necessity, that you prove that somehow you are staying close enough to the central path that you'll arrive at the solution. So if you're curious for details, I think last year, the last time we taught it, which was fall 2016, we did 2 lectures on it, and the second lecture gave the details of these steps. Yeah, it's a very good question. We're not really, I decided not to kind of spend time on that this year. Yeah.
So just to clarify something about the question beforehand. So when we pick our x naught, so we're taking that to be strictly feasible with respect to inequality constraints. Are we also picking it to satisfy x equal b, or are you saying that we don't necessarily need to because of the residual stopping?
Yeah, so I think the best thing for me to do is just to add a line here that clarifies that so we can not be confused. But it's a fine question. We do not need to start with ax equals b. By strictly feasible, I just meant hi of x is strictly less than 0. Nobody's stopping you from doing that. If you did that, then your life would be easier because this would be 0. But if you did that, then also it might require an expensive kind of feasibility program to solve before you start the algorithm, right? You have to find some x that satisfies all those equality constraints, and then the hi of x less than 0. So you can start the primal dual interior point method infeasibly from the primal, and it'll run fine. So thank you. I'll make a note just to kind of add to the slide to clarify that. The history I already went through last time, so I guess we don't need to go through that anymore. I'll just repeat that somehow this is like a high point of achievement for, for optimization in the 70s and the 80s. And maybe I'll also just comment a bit more briefly on the fact that there are many variants of the primal dual interior point method. This is just kind of one version. There are many versions. There are many, many different things that you can say about them in terms of their convergence behavior. And there are entire books on the primal dual interior point method. So Stephen Wright has a book which is called Primal Dual Interior Point Methods, and it's a famous book. He's a very famous guy in optimization. There are whole courses taught on the primal dual interior point method. So this is like the tip of the iceberg in some sense. And this method for SDPs, I'd say, is a particularly impactful and impressive but very complicated combination. So taking, as you can imagine, somehow if I had an SDP and all my variables were matrix valued, this system is a lot more complicated. It's not as simple as what I wrote down, and the steps are a lot more complicated. So then the update steps actually are they're much more subtle. You need to take kind of much more care in making sure that you stay close to the central path for SDPs. So making sure that you bounce around and don't diverge for SDPs is itself like a major topic of study. So there's a lot more to learn in case you're curious. So let's just finish by talking about LPs. I wanted to give you some perspective on how the Berry method and the primal dual method differ. So let's talk about standard form LPs. Right, so this is an LP in standard form. I have equality constraints, AX equals B. I have positive or the non-negative orthant constraint on X, and the criterion is just this simple linear function C transpose X. It's dual, which I'm not sure that if we somehow, I know we did the dual of kind of generic form LPs, not in standard form. I'm not sure if we did standard form LPs. This is not a bad thing to memorize. I somehow think that like there's a very beautiful symmetry between this problem and this problem. So it's not a bad thing to memorize at all. The dual is as follows. Okay, so maximize B transpose V subject to A transpose U equals C, and U is bigger than or equal to 0. So also a standard form LP. This guy here is also standard form. So what are the KKT conditions for the standard form LP? So when do I have a solution here and a pair of dual solutions here, or a dual solution UV here? They have to satisfy the KKT conditions. And stationarity, okay, is just this guy. A transpose V plus U is equal to C. That's stationarity. Compound slackness is Xi Ui equals 0. Right? That just comes from this condition. Primal feasibility is AX equals B and X bigger than or equal to 0. And dual feasibility is just U bigger than or equal to 0. Okay, so these are the KKT conditions for a standard form LP. And if I solve these, then I have primal and dual solutions in these problems. And just an interesting aside, because we didn't talk about the simplex at all, but again, if you're curious, there's tons of literature out there. What any interior point method does, so the Berry method or the primal dual interior point methods, or all of the variants of those that we didn't talk about, is that they maintain the first, the third, and the fourth conditions, and they try to satisfy the second in the limit. Right? They perturb this. They change this to Xi Ui equals minus 1 over T, and kind of in the end point of the algorithm, they try to get Xi Ui equals 0 by making T very large and solving a sequence of these perturbed problems. What the simplex method does is it actually maintains a different set of conditions. It maintains actually the first three. And it tries to maintain at the end of the algorithm the fourth. It tries to meet the fourth. So they satisfy the KKT conditions sequentially, but in a different way. The simplex algorithm bounces around somehow the feasible polyhedron. It bounces around the vertices of the primal feasible polyhedron. And one way to see that is that it moves in a subspace defined by these linear systems, and it tries to eventually arrive at a vertex that satisfies these orthant constraints subject to these linear systems. So let's now look at the perturbed KKT conditions. So for us, Hi of X was actually minus Xi. So the perturbed complementary slackness was Xi Ui equals 1 over T. And what do our two different interior point methods that we learned to do? They take this linear system, or this nonlinear system, right? Because I have the product Xi Ui. They take this system, and they solve it with Newton's method in different ways. The Berry method eliminates U, so it substitutes in for U 1 over T times X, or Ui is 1 over T times Xi. And it tries to solve this nonlinear system. So we're going to maintain these positivity constraints always through backtracking and initialization. So we care about these equality constraints. And after eliminating u, the stationary condition looks like A transpose V plus, this is just a vector that is in every component 1 over t times xi. So I'm writing it as diag of x inverse times 1 over t times the 1's vector, minus c equals 0. And primal feasibility is just ax minus b equals 0. The primal dual method does not perform that elimination, and this is the nonlinear system it tries to solve. Okay, just taking, again, the first 3 equalities here. So the Berry method, it performs this Newton update. Okay, so it linearizes this function r, and it solves this system at every iteration in order to find the direction delta x delta v to update my x and v variables. And it takes a step in this direction with line search, and it does that until convergence, until I arrive at a point that actually, for a particular value of t, solved this system, or very, very nearly solved this system. Okay, and then I update t. I multiply t by mu. That's the Berry method. The primal dual interior point method solves a different system, so this bigger system. And I guess we're not exactly, we don't have tons of time left. I won't go through the details for where this Hessian came from, but it's just kind of straightforward differentiation of this system. So it solves this bigger system, and it takes one update in x, u, and v together, uses backtracking in order to kind of maintain the right positivity constraints on x and u. And then after that one update, it updates t. It does not iterate until conversions. Okay, so those are the methods kind of at a glance for this linear program. And here's an example of that I took from Board and Vandenberg to highlight how they work. This is a standard form linear program with 50 variables and 100 equality constraints. And the Berry method, here was the Berry method, by the way, over a bunch of different values for mu. Okay, and I don't know if you can see, it's maybe a bit small. When mu is 2, the Berry method took a total of 80 iterations to decrease the LP criterion to a kind of a suitable duality gap, which was about 10 to the minus 4. When mu was 50, it took about 30 iterations. And when mu was 150, it took about 40 iterations. So this is the comment we made last time, which was that the Berry method is a bit robust to this choice of barrier parameter. It doesn't really matter so much. You know, we ended up somehow bouncing between 80 and 40 as we multiplied mu by a factor of about 100. So it was really not that big of a difference. Here's the primal dual interior point method. Okay. Here's the primal dual interior point method for mu equals 10, so just one value of mu. And if we look at the number of iterations it took to get to the same duality gap, 10 to the minus 4, it took about, takes about maybe between 15 and 20 iterations. Okay, so it's a bit faster than the Berry method, and it converges to very high accuracy very quickly. So after about between 25 and 30 iterations, it's at nearly 10 to the minus 10 duality gap. Okay, so to be honest, I was plotting here the surrogate duality gap, and recall that this is somehow only really a valid interpretation of the duality gap if the iterates are approximately feasible. And so here was the feasibility gap. So we actually stop when both of these are small. Okay, and this thing gets made very, very small in a small number of iterations. So after iteration 20, we're pretty much feasible, and we're fair at assessing this as the duality gap. So I guess the takeaway is that it's faster to converge to high accuracy. So yeah, this was just a comparison of how these methods performed as we increased the number of inequality constraints. And we saw that the convergence rate for the Berry method, it was something of the form log of m over epsilon. That was roughly the convergence rate for the Berry method. So as you increase the number of inequality constraints m, we should expect the number of iterations we need to converge to high accuracy to grow very slowly. That's what this plot is showing. Okay, it's growing very slowly with m. And in this case, we're actually running the primal dual interior point method to to get much higher accuracy solutions. So I think it's like almost 4 orders of magnitude higher accuracy solutions than the Berry method, and you can see it still decreases only kind of gracefully, increases only kind of gracefully with m. So it increases what looks like a little bit faster than logarithmically, but that's actually more of an artifact of the stopping point. So we're running it to much higher accuracy here. So again, a rough conclusion somehow is that the primal dual method is often more efficient. It's often going to get, it is worst case going to get a convergence rate like this, but for several problems it'll get a superlinear convergence rate, so faster than this. And that's what you'll see whenever you call your favorite solver that's kind of some standard solver. It'll be using as an interior point method the primal dual interior point method. Okay, so that was it for interior point methods. You guys survived, and next time we'll talk about quasi-Newton and proximal Newton next week, and I won't be here. So I will see you guys then in a week.